JD. That's what I need to do.
Yeah, just mute that YouTube.
I'm unable to find the button to unmute.
It's okay. We don't hear an echo. Don't worry about it.
Okay.
Yeah, just mute that.
I did. It's fine. So let me start. So hello everyone. Good evening to all of you here in India, and good morning to Frank there in US. So let me begin this webinar by welcoming you all to this. This is a first of a kind, a joint webinar series between Indian Institute of Science, Bangalore, and Tata Institute of Fundamental Research in Mumbai. The idea behind this webinar is me and Professor Jyotisman Das Gupta felt the literature is flooded with large number of papers, and today's research is all about H-index and a large number of papers. But however, the students, a new grad students, when he just simply look at, ask him to go back and read about what has been done before he begin his research, they seems to be lost because the amount of information available in the publications. So they somehow do not really read the right paper, and they come back with a very confused sort of a statement. So we both felt it is necessary to invite a leading expert from around the world to pay us a visit once in a month, discussing in a very detailed the complexity of the subject and forefront research ideas in a given area. So this lecture series will be 2 at a time, and they're tutorial style. So we also hope to increase interactions between many institutes within India, which will motivate the young minds to work on a bigger research goal. So we will do this Zoom webinars for the 2 sessions. One will be hosted by ISC and another hosted will be by TIFR. Now I request Professor Das Gupta to talk a little bit about sponsors about this webinar. JD, please.
Yeah, thank you, Satish. That was a very nice introduction to the idea. And we are very lucky that ACS, the American Chemical Society, found the idea pretty appealing, and they have actually fully supported us for this entire series for a year. But apart from their support, it's also important that I would like to mention that ACS has also given out for all the attendees in this session, if they want to sort of apply for an ACS membership, they would give a 50% discount on the membership fee. So that is also something that they would like to, sort of promote the promote ACS's association with chemists in India. So through this is another way of associating with the different kinds of events that Indian scientists are organizing within the community here. So thank you, ACS. Thank you, Deeksha. Thank you, Ajay, for doing this. And I would like to now get back to Satish to actually formally introduce Professor Frank Spano.
Okay, thank you, JD. I think to start this series, we have invited a leading expert, Professor Frank Spano, a leader in a computational spectroscopy of a conjugated materials from Temple University. Frank, there is no need of introduction for the today's speaker. He has done some remarkable work in a field of computational chemistry in a conjugated materials. I'll just briefly read about his he did undergraduate in 1982 from Lehigh University, and then he moved to Princeton, where he did his PhD in 1988, and followed by he did a postdoc in University of Rochester. So currently he is a professor in Temple University. Frank's excellent work in the field has been recognized with several academic rewards. He's the Honors Professor of the Year, the Italia Air Foundation, a Distinguished Teacher of the Year Award, and CST Outstanding Research Award. With this brief introduction, I invite Frank to begin his tutorial.
Well, What can I say? This is an incredible honor to be talking at one of the world-renowned institutes and research institutions, ISC. So thank you so much, Satish and JD. Did I say your name correctly? This is, like I said, a great honor. If I appear a little bit tired, I think everyone might know the reason. There's a little bit of a political thing going on in the US right now, and keeping us all very, very stressed out. So, but this is going to provide a wonderful little distraction, hopefully, for the next hour or so. And so, yes, thank you again. And I'd like to talk about some of the stuff I've been doing now for more than a couple of years, based on H&J aggregates, and I'll explain everything shortly. And particular theme of today's talk will be the influence of vibronic coupling. So there's a well-established theory due primarily to Michael Kasha, who just recently, a couple of years ago, passed away, very close to 100 actually. And the theory was in the late 50s, but it did not include vibronic coupling. It was based entirely on electronic coupling. And basically today's talk will be an extension of Kasha's theory. So as Satish told you, I come from Temple University. And so I think it's appropriate to start with a little bit of background information. Where the heck is Temple, right? And so in the United States, hold on a second, I'm trying to fix this grid so that it doesn't, okay. So Temple is fairly old university by US standards, young by almost everybody else's, established 1884. It's a Research One university recently. That happened maybe 7-8 years ago. A large institute of about 40,000 total students, 30,000 roughly undergrad and the rest graduate students. And as you can see here, we're on the east coast of the US, up in the Northeast, kind of sandwiched or nestled between Washington and New York. And so that's where I'm broadcasting from right now, halfway around the world to you guys. So I've been literally obsessed, I guess is the correct way of saying it, with organic materials over, for many years, and specifically pi conjugated organic systems. And here's just a few of the molecules that I've been interested in, and not for the individual molecules per se, but mostly for what happens when molecules talk to each other in the solid phase, either crystal, thin film, aggregate, whatever. And of course, they can couple to each other electronically. And while they do this electronically, they're also vibrating and they're experiencing disorder. And so it's a very, very complex and fascinating problem. And you may notice, in fact, I'm sure everyone notices the common theme between these molecules, which is an alternating double, single, double bond, a so-called pi conjugation. And why that's interesting is because when you have a system like that, you have essentially a semiconductor, right? So you have a pi star transition within a valence band and a conduction band, right? If you come in with a photon, roughly 2 to 3 EVs, you'll promote the so-called pi star transition, the elevation of an electron from the HOMO to the LUMO level. And this gap is very sensitive to the length of conjugation. So it's very tunable, either through that or chemically, for example. And 2 to 3 EVs, of course, is a visible photon. So now you have the ability to create a semiconductor, right? So you can create this electron hole pair, which is often called an exciton. And that exciton can travel, right, and march from one molecule to another. And hopefully, for example, in an OPV device, we can extract some work from it. And so I got a little mixed up in my order here, but the reason, the main or the commercial motivation for such materials is, of course, in these various devices, based on their semiconductor nature, you can make field effect transistors, you can make light emitting diodes and so on. And so you get all these wonderful modern technological devices that, if you dig deep, you'll probably find a pi conjugated organic chromophore doing something interesting in there. And so, of course, we weren't the first to take advantage of these systems. Nature always wins. And here's just a beautifully symmetric complex. This is a light harvesting complex in purple bacteria. It's a very primitive organism. But anyway, this ninefold or so symmetric assembly of these chlorophyll molecules is able to absorb, a solar photon and then shuttle it or harvest it or direct it towards the reaction center Okay, and this is quite a remarkable system. And of course, we get jealous and we want to say, wow, wouldn't it be great if we could make that something like that too? And so we try to fabricate organic photovoltaic materials, or solar cells for short. And for the absorber, we use simpler systems, well, in some ways simpler. And here's an example of a polymer absorber, which is called poly-3 hexylthiophene, or P3HT for short. And it acts as a very efficient solar absorber, so it can also grab a solar photon and shuttle it all the way down to an interface, say with a fullerene, and then have charge transfer, and then exploit, use those charges to generate current, and so on. And so this is the kind of sure.
Sorry, I have a question. So these are two completely different functional components, right? One for photosynthesis, it's for just light energy sort of migration or exciton migration. And in this case, what you're comparing it to something which has both the jobs of light harvesting and charge generation, right?
Well, so, I'm just showing the half of it, because this is the absorbing material, but you need to put a fullerene in it in order to get a solar cell. I actually had a slide that showed that, but I took it out because I thought it was too long. But yeah, good point. And so anyway, the harvesting, or the rate of excitation energy transfer, is a very important topic. It's a very rich topic. It's very complicated. You may think, oh, sure, it's just once you evaluate the electronic coupling between neighbors, you pretty much have the understanding. But it's far more complex, because, as I said earlier, they're not just exchanging electronic energy, they're also vibrating while they're doing this. And of course, there's always the ubiquitous presence of disorder, which can come in many, many, many varieties. And of course, thermal fluctuations, or so-called system-bath interactions. So it's a fascinatingly complex problem, and many, probably thousands, maybe 10,000 papers devoted to it over the years. And so what I want to talk about today in this first talk is it's a kind of simple endeavor, a simple theme, but it will take us in many directions. And basically, how much can we learn about the underlying nature of the important ingredients which contribute to exciton transfer, like the electronic coupling, the disorder, coherence, and so on? How much can we extract from very simple optical probes? I mean, many of you are aware of complex optical probes like 2D spectroscopy and various nonlinear forms, but I've always been fascinated with the very, very simplest of things, and trying to get as much information out of the simple things before kind of, moving on to the more difficult or more complex thing. And so we'll be focusing on simple things that an undergraduate measures pretty routinely in PChem lab, or even in organic lab, which is UV-vis, steady state absorption, right? Or fluorescence, or what I call photoluminescence. And we're looking for spectral signatures, okay? And so the outline of today's talk and tomorrow's talk is the following. I'm going to introduce the classic Kasha theory, or the Kasha-Frankel theory, which is the first real attempt to try to correlate structure, packing, for example, with photophysical properties, absorption, emission. And this goes back to the late 50s. So as I mentioned earlier, Michael Kasha. It focuses primarily on Coulomb-coupled aggregates. And I'll explain that in great detail coming up soon. And then I'll go into the extensions that I've made to this theory based on vibronic coupling, as I mentioned earlier, and introducing a new Hamiltonian, which incorporates vibronic coupling, which is called the Frankel-Holstein Hamiltonian, and then looking for additional signatures based on the vibronic coupling. Okay. And then lots of applications will appear throughout the talk. This is a tutorial type talk, so I want to keep it, in that mode. In tomorrow's talk, we're going to extend the theory in another direction, and that is in the direction of intermolecular charge transfer. As I mentioned earlier, Kasha's theory is predicated entirely on Coulomb coupling, but both types of coupling exist, especially in very tightly packed materials like pi stacks. And so we'll get to the very interesting concept of interference between short and long range couplings, and then the possibility of having a different type of aggregate based on those two, called an HJ aggregate. And then the possibility of a null aggregate. We have some null aggregates experts in the audience. And then implications, and again, lots of examples. One thing I do is obviously I do theory, but I am just obsessed. I mean, I don't do anything unless I can really try to explain some observation. So what is the impact of aggregation? So there are many examples in the literature of what happens when you take a molecule, for example, distyrylbenzene, and you put it in solution, methanol, for example, and then you measure its UV vis, you get this nice dotted spectrum, and then you measure its fluorescence, and you get this spectrum here, and everything kind of looks nice and almost textbook-like with a vibronic progression. And then you add a little bit of water, right? And the bad solvent actually encourages aggregation, and you look at what happens to the spectroscopy of these little aggregates, which form in this kind of herringbone packing arrangement, and you can see dramatic changes. And I'll point to a dramatic blue shift of the absorption spectrum, a restructuring of the emission spectrum. You notice how the ratio between the 0,0 and the 0,1 is dramatically different than it was for a single molecule. These are the kind of things that we're going to pay attention to as vibronic signatures as we continue. Another example that I've had the pleasure of dealing with over the years is deals with these class of molecules called carotenoids, and they're very ubiquitous in nature. Here's just a couple of them. They all have the conjugated system, of course, and they have 4 of these so-called isoprene units with various end groups, and they are responsible for the beautiful red color of tomatoes and the color of lobsters and flowers, and so they're very important in nature. They're photobleachers for photosynthesis, so they protect you against photobleaching. There's all kinds of functions. I just want to point out a study that occurred probably 20, 30 years ago, or 20 more like, on lutein and lutein diacetate. So it's basically the same structure, but you change the R group. And if you look at what happens in solution versus aggregate, that's what we're concerned with. These types of molecules, they pack in these chiral type linear aggregates, or at least that's the simplest way to envision this. And how do we appreciate that is from the UV vis spectra. So here's the monomer in solution. It's this beautiful vibronic progression, right, in acetone. So it's a single molecule. And I just show one curve here. Both of these molecules, either with the R equal H or the acetate, basically have the same monomer spectrum. Now, what happens in lutein when you add water, as again, you add water, that's just a coincidence, I guess. You create this huge spectral blue shift, right? And you get this blue spectrum. But if you do it to lutein diacetate, you get the red spectrum. So both of them are notably different from the monomer spectrum, but in very different ways. And how can that be? Another example that I've spent a lot of time on is in this P3HT polymer that I mentioned with connection with OPV cells.
Frank, another question. I'm sorry, I'm stopping you. Could you just go back one slide? This is something that we've been working on recently with lycopene. So I just had a quick question. Maybe you'll come back at the theory part when you explain the computational signatures. This particular blue shifted aggregate, right,
Mm-hmm.
has a tail at 22,000. At 22,000, the blue spectrum has a feature there. Would you also explain that in the talk?
Sure.
Yeah.
You know, features, I will just say one thing. Well, there may be multiple origins, but I would say you got to be very careful in these types of experiments when you have a feature which overlaps the monomer, right? Because you don't know whether that's leftover monomer or a feature that's intrinsic to the aggregate.
Right.
So without additional experiments, it's just speculation.
It's very difficult. Okay.
And so, yeah, so, you know, as a theoretician, it's really hard to, this is probably the hardest part of theory I tell my students is you don't know what to believe experimentally because you're not an experimentalist. Right. And, you know, it's hard. Okay. Anyway, okay. So P3HT, of course, motivated by its commercial use in OPV cells. In solution, it has absorption, which is basically featureless. There's not really much going on. And then emission is this nice vibronic structure. But if you spin cast it from some solvent, so you make these thin films, you see, again, dramatic differences. You see a serious redshift in both spectra, you see the development of vibronic structure on the absorption spectrum. And again, just like you saw in distyrylbenzene, a complete restructuring of the relative intensities of the emission peaks, the vibronic emission peaks. These are all clues as to some underlying common theme, and that's what I want to bring out to you. All right, so we're going to start with Kasha, and this is the Kasha-Frankel model because Kasha used Frankel's exciton model to develop his theory, and it was a theory which was trying to explain something else, enhancement of photoluminescence. That's the name of the paper from 1958. Beautiful paper, short paper. In those days, they wrote short papers. Anyway, he recognized two types of aggregates, and he didn't call them H and J. It later became known as H and J, but basically the idea is if you have two chromophores with transition dipoles, let's say along the long axes, you can imagine a side-by-side arrangement. And in a side-by-side arrangement, and if you, the Coulomb coupling will be positive. So you imagine each of these is a little oscillating dipole, and they couple together with this common Coulomb coupling expression side by side, and it would be positive. And the reason, one way I always tell students it's positive is just imagine two, I don't know if you can see my fingers, imagine two bar magnets. And if you put two bar magnets, anybody who's played with bar magnets like me when they was a kid or whatever, you put them side by side, obviously the north and the north are close and the south are side by side, and they repel each other. It's a repulsive, positive energy, right? But if you were to take one magnet and slide it along its long axis, eventually one of the north poles and south poles would be adjacent, like you have here, and you would have an attraction. And so if you slide one molecule against the other to create this head-to-tail arrangement, you have a change in sign of the dipole-dipole coupling, and we call that a J aggregate. And the changes in coupling are manifest in pronounced changes in the absorption and emission spectrum. So what Kasha recognized is that if they're side by side, if this coupling is positive, you'll see a blue shift, a shift to higher energy of the absorption peak, like some of the examples I showed, and you'll see a diminishment of or attenuation of the radiative decay rate to make a subradiant, so smaller than a single molecule. And exactly the opposite happens in a J aggregate. With the negative coupling, you basically induce a red shift and what we call superradiance. And another thing that's interesting, if you look at the Kasha papers, he never says superradiance. That's a term. A lot of the stuff, the terminology, of course, followed his pioneering work. The classic example that kind of started the whole thing going was some observations by Scheibe. Now, this is a 1970 paper, but he goes back to the 30s, along with another scientist called Jelly. And so if you wonder why they're called J aggregates, it's because of Jelly, J-E-L-L-Y. And Jelly and Scheibe were, I guess, independent discoverers of this phenomenon. If you take pseudoisocyanine chloride and you dissolve it in some friendly solvent, you'll get this monomer spectrum here. Again, notice this pronounced vibronic structure. But if you change a pH or change temperature, do something to influence aggregation, you'll see the development of this very sharp, narrow, redshifted peak. And this really began it all. It's a huge, huge change in the optical properties. So that's the J aggregate, again, redshift. Now in the H aggregate, another example, as I showed you earlier, would be this distyrylbenzene, and they pack in this herringbone side by side. We know that from X-ray studies. And you see now a very strong blue shift. But again, this vibronic reshuffling of intensity. And so spectral shifts arise from excitonic coupling. That's Kasha's contribution. That's huge. But I always worry because spectral shifts, I think we all can kind of realize or appreciate that they can come from other sources. And the very famous one is called the non-resonant or gas to crystal shift. Whenever we take a molecule from the gas phase and crystallize it, there's always a non-resonant redshift usually. And so you might think, well, what if I have a H aggregate with and so I crystallize it and it has a very large redshift due to gas to crystal, but it is an H aggregate, the overall shift will still be red. And you're going to say, oh, it's an it's a J aggregate because of Kasha, but it's really an H aggregate. So it's confusing. And, spectral shifts can't be relied on for determining J or H, right? And that's important because once we know J or H, we make inferences about how they're packing, right? And so let's go back to Kasha now and understand a little bit more about that excitonic induced shift, red or blue. And let's begin with the H dimer. And this is a picture that Kasia also has in one of his papers. And you start with a ground state, which is kind of boring. You have two molecules that are not excited. If you excite with a single photon, you can create two possible states. One state, you have a left molecule excited, and the other one, you have a right molecule excited, right? And they're completely degenerate. These are the monomer-like states. And of course, if you measure absorption, you'll see the monomer absorption spectrum. However, they're close enough, right? And they're going to couple with a positive coupling, as we just said. Remember the two bar magnets. And so once you introduce the coupling, it removes the degeneracy, and you get split states, right? You have two states. One state is in phase, and that's the state that has, well, a higher energy, and the out of phase state has lower energy, and that's because of the sign of the coupling being positive. So basically, simple quantum will tell you that you have an in phase and out of phase state. Because the state is in phase, if you actually look at what that means for the dipole moments, you'll see that the transition dipoles are aligned in the upper state and anti-aligned in the lower state. Now, if you're an electromagnetic wave coming in on the system, you're going to grab, this has a net dipole, right? So you'll grab onto this state, and this is the state that absorbs. And so if you now look at the absorption spectrum, you see a blue shift because the monomer is here and the dimer is here. So you see a significant blue shift, which in this case is equal to JC, right? The total splitting is 2JC. This bottom state will not absorb at all because there's no net transition dipole. Now, if you look at a J aggregate, all you do is flip the sign and everything flips over. So now the in phase state, where they're both aligned, is on the bottom. And so now you have a redshift, right? And the upper state is optically dark. And so that's the idea with dimers. But dimers are usually insufficient to explain larger crystal structures, pi stacks, and so on. So we got to take it a step further. And the next step would be to do a linear aggregate, right? And if you look at this, this is just 4, but you can imagine a long chain of these molecules. And you see, you can identify locally excited states, n equal 1, n equal 2, n equal 3, and you can imagine they're all coupled through, let's say, a nearest neighbor Coulombic coupling, just like we saw in the dimer, right? And here is the famous Frankel-Hamiltonian, again, which is the basis of Kasia theory. And here I have just a simple term representing the monomer energy, and then a straightforward kind of just nearest neighbor coupling between n and n plus 1. You can extend this to, you can expand this to beyond nearest neighbor very easily, but I just want to talk about the essentials here. And so this is the Hamiltonian you would use, and you would quickly find through analysis of this, if you looked at the eigenfunctions, they're the so-called Frankel excitons, which are delocalized. So you see a sum over these local states with a phase factor, which defines the wavelength or the wave vector k, right? And so n, capital N throughout the talk, that's always a number of chromophores. So n would be 4 in this example. So these are delocalized. And what you find is that the k equals 0 state captures the bulk of the oscillator strength. Just like that in-phase state we saw with the dimer, that generalizes to the k equals 0 state in a long monomer. And so I want to talk a little bit, because it's such an important aspect of these aggregates. What does it mean to capture all that oscillator strength? So let's take a further look, a closer look at these Frankel excitons in one dimension. And here's that expression I just showed. And now let's imagine an aggregate. In this case, it's, 6 molecules. And let's look at that k equals 0 state. Again, a little bit more closely. K is 0, of course, the phase factor goes to 1, right? Uniformly for all. And so indicated in this cartoon, the red molecule is excited. So that's n equal 1, n equal 2, and so on. And the vector indicates the direction of that corresponding transition dipole. So you see in the k equals 0 state, you have a 1 over root n because it normalizes the state. And then you sum up all of these various local states. And if you realize that, of course, if you sum these red vectors, you're going to get a factor of n, but that will be reduced by root n in the denominator to give you an overall root n in the sum. And so the transition dipole of the aggregate for the k equals 0 state is enhanced by root n times the molecular transition dipole. And that's very important because that's the source of what we call superradiance. Another state here, which is not k equals 0, let's take k equal pi, the state where we have the most number of nodes. And here the phase factor e to the pi n reduces to -1 to the n, right? So every time you move the excitation, there's a phase change, right? Minus, plus, minus, plus. And of course, If you subtract a dipole in the positive direction, that's like adding one in the negative direction. I just rewrote it to reflect the phase of the transition dipole. Now you can easily see that if you add up those red dipoles, you get a big fat 0. There's no way this can absorb, okay? If you did this little exercise for all of the non-zero K values, you would find similar cancellations. And in fact, the only state that adds up to a non-zero value and a enhanced non-zero one nonetheless is K equals 0. And so we can represent that mathematically by saying the transition moment is a Kronecker delta K0 with this enhanced dipole moment here.
Question here. So there is one question from one of the attendees who is asking, why is it restricted to nearest neighbor only?
I'm just trying to make a simple argument here. What I said now has absolutely nothing to do. If you extend it to beyond nearest neighbors, you would find exactly the same thing. The symmetry of the problem would be such that only K equals 0 is absorbing. Now, if you extend it, what I didn't say is that I'm also assuming what we call periodic boundary conditions. So the first and the last molecule are connected like in a ring, right? If you made open boundary conditions, there'd be some changes to this, and it wouldn't just be one state, but it would be mostly the nodeless state that would carry the bulk of the oscillator strength. Okay, I'll show you some examples later. All right.
Another question, Frank. Sorry. If you go back one slide, this is from my side. The question is from my side. Could you just explain again what the exchange Hamiltonian terms mean, in the sense that JC times, those are the densities of so those are
okay,
Kets and Bras? Yeah.
So basically, what this Ket bra is saying, it's an exchange of energy between n plus 1 and n.
Okay.
Right. And so that is dictated by this Coulomb interaction. Right. So this is purely nearest neighbor. I'm just trying to give the simplest here, but of course there's changes when you put beyond nearest neighbors, but they're only superficial changes. The important intrinsic, the basic appreciation for this can be captured already with just nearest neighbors.
Okay, one more question from the chat box. If the transition dipole moments are not parallel, it means they are oriented in some angle. What would happen to the signatures on aggregate?
Very, very good question. Yes, you're anticipating all the next layers. Yeah, that's a great question. If the dipoles are not, what I'm showing here again is the simplest construct where there's one molecule per unit cell, right? So they're all related by translational symmetry. If you chose a situation where they were not parallel, let's say you had two unique orientations where one is, let's say a unit cell had two molecules and each molecule in that unit cell was differently oriented, then you would have two states which would acquire oscillator strength, and you would have what's called Davidov splitting. So that's another complexity beyond this, but I want to, it's a great question. But yes, I'm assuming that all the molecules have just, that the aggregates have one molecule per unit cell, and therefore a single unique transition dipole. Okay? All right, so we're getting to the good part now. All right, so what happens in a linear aggregate if you look at the exciton dispersion? If you take a J aggregate, this little figure here shows, and we've all seen this, right? In PChem, this is a particle in a box, right? These are, I took an n equal 20 aggregate and I just graphed out the various excitations, right? And the lowest to highest, the nodeless state, K equals 0, and the K equal pi. Now, because it's a J aggregate, again, the lowest state is the state with no nodes, and the highest state, it has all of, the most nodes. And you can see from the structure of this diagram that the single molecule absorbed here, again, the K equals 0 state, which does all the absorption, is much lower in energy. And in this case, the bandwidth is 4 times the nearest neighbor coupling. So the redshift would be 2 times the magnitude of the coupling in this case. Okay, so this is the J aggregate with a negative coupling, nodeless state on bottom, redshift. Now, when you change the sign of the coupling to make an H aggregate, you just take your particle in a box and you flip it over. So now the nodeless state becomes the high energy state. And of course, that's responsible for the blue shift, right? The other attribute, photophysical attribute of J and H is the emission. So for a J aggregate, it turns out that the K equals 0 state is the main absorbing state as we showed, but it's also the main emissive state because the radiative decay rate goes as that very same transition dipole moment squared. And as I showed you earlier, the transition dipole went as root n. So when you square it, it becomes n, and that's known as superradiant emission. So the emission comes out a lot faster compared to a single molecule, okay? And now, if you look at an H aggregate, you might say, well, okay, the emission comes out the same way. What's the big deal? You excite this state and it emits there. But because it's an H aggregate, it means the nodal states on top. You have all these states that are high density, you know, if you have a large aggregate. And so it is there is a very, very rapid competing mechanism, which is called intraband relaxation, whereas when you excite this state, it'll very quickly, on the order of probably less than a picosecond, populate the bottom state, right? And this is actually known as Kasha's rule. It's a different rule, but you basically start your emission from the bottom of the lowest excited state. In that case, you would see nothing because this is the state with all the nodes where the dipoles interfere with each other, right? So that's the basic Kasha theory. And if you do a quick calculation of that Frankel model, and you plot the absorption, you see a J aggregate, it red shifts as you increase the coupling, whereas an H aggregate, you blue shift as you increase coupling.
Question, sorry. Go back one slide more. Yeah. So there's a chat box question that says, what are the dots? What do the dots represent here?
The dots? You mean these?
Yes.
So this is the wave function, right? So these are the coefficients in that expansion over those n states, those n equal 1, n equal 2, n equal 3. Now notice, I know you guys are way ahead of me. I'm actually showing you something with open boundary conditions. I'm going to be honest now, because you guys are, I can't, and so you see this really particle in the box like behavior. Of course, we know there are boundary conditions in particle in the box. It's not periodic, but again, it's a small effect, and it's not going to change our main
Okay.
here.
Okay. And a question here on this slide. It was too quick for me. What you just did, where you just plotted the absorption spectrum?
Yeah. This is just the absorption as I increase the coupling in a J and in an H. Right. And so as you can see, that redshift corresponds or is dictated by the magnitude of the coupling. Right. So as I increase the coupling, I increase the redshift, right, or I increase the blue shift. So basically, what people do, that follow Kasha theory, is they'll take the spectral shift. So the monomer will absorb here, right, and then they'll say, oh, the blue shift is 1,000 wave numbers. And then they'll equate that to twice the coupling, and they'll say, oh, we know the coupling now, and now we know it's positive, so we can say that it's face to face, and it's this distance from, it's this intermolecular distance because the coupling is this magnitude. In other words, they're basing everything on the spectral shift. All of the structural excitonic information is coming from this one spectral shift, which I maintain not all the time, can be misleading because there are other sources.
And the width of the spectrum, what did you put to?
I just use a nominal value.
You don't have any vibronics here. You just has a pure
no vibronics yet.
Transition.
I haven't yet introduced the good part yet.
Right. Okay.
Spectral shifts can be misleading, as I just said, and so in some cases not so much, because here's a very strong blue shift compared to the monomer, and as we'll find, yes, that is an H aggregate according to Kasha. Now here, look at this red spectrum, you see a red shift, right? Now, if you were going to apply strict Kasha theory, you'd say, oh, it's a J aggregate, but it is not a J aggregate. I will show you later that it's a weakly coupled H aggregate. And so what we need to do, as JD just kind of introduced, we need to incorporate vibronics. We need to incorporate vibrational coupling. This mode here, which is represented by this pronounced progression around 1400 wave numbers, is very ubiquitous amongst very different types of conjugated molecules. And basically what it is, it's the single bond is shortening while the double bond is lengthening, right? And as this thing vibrates. So it's a vinyl stretching mode. When there's aromatic rings, people also call it the aromatic quinoidal mode. But it's amazing that in these very different structures, these are experiments, of course, that you see basically a very similar energy, 14 versus 1200, and very similar vibronic progressions with regard to the relative peaks. And so it's a ubiquitous feature. How do we incorporate it into a model which will expand Kashas? And so that's the idea. And when you do that, can you recognize new signatures for H and J aggregates beyond the spectral shifts of Kasha that are more reliable? That's the goal. And so simplest way to incorporate vibrations in electronic or vibronic coupling is to have harmonic wells for each electronic state. So a S0 and an S1 state. When you excite Frank Condon manner, right, you go vertical, and then in a simple sense, this will relax to the minimum, and this amount of relaxation energy. If you normalize that relaxation energy to a vibrational quantum, you get a dimensionless factor called the Huang-Reis factor. It's a measure of how displaced these two wells are. And so this is the dimensionless factor. Once you know the Huang-Reis factor, you can predict the absorption spectrum. The absorption spectrum consists of all the transition originating from the zero quantum state in the ground electronic well to various states in the excited well with different quanta. So 0, 0, 1, 0, 2, 0, and so on. Each one is a peak, gives rise to an absorption peak. And if you know lambda squared, you can work out the relative intensity through the so-called Frank Condon factor. See, it just has the lambda squared in it, the Huang-Reis factor. And I want to just highlight lambda squared equals 1. When the nuclear relaxation energy is equal to the vibronic frequency, you have lambda squared equal 1. And that's important for what follows, because when that happens, and you look at this Frank Condon factor, if you looked at it, these two peaks are exactly equal when lambda squared equals 1. And that's important theoretically, because once they're equal, it's very easy to appreciate when something happens to distort the progression. If we add in intermolecular coupling, will that change these frequencies? It's easy to see changes when they're equal. So lambda squared equal 1. And of course, if you look at emission, you have this mirror image, which is textbook-like emission. So vibronic progressions in the absorption and emission dictated by the Huang-Reis factor. Now, another appreciation for vibronic coupling comes from the transport process itself. And I often use this metaphor of a bowling ball. We're all familiar with how quickly a bowling ball will proceed down a hardwood alley floor, right? I mean, it's very hard surface, which you can envision as a series of very, very stiff springs. So stiff that the ball basically does not compress any of these springs. There's no real exchange of energy between the ball and the potential energy of a spring. And so everything you put into the ball, all the energy is pretty much kinetic energy, so it goes fast. But if you want to see what happens, the metaphor with an organic soft material is that you don't have a hard, a weak coupling between the two because of the.
I'm sorry. Jayashree has a question. Jayashree, we'd like to turn on your audio. Unmute.
Sorry to interrupt, Professor. So I had a couple of questions about the HR factors slide. If you can go back one slide. Right here. So one of the things I understand, if I understand correctly, is that you can define this HR factor as long as the two surfaces have the same set of frequencies. Is that correct?
Yes.
And
yes, oftentimes.
Yeah,
and that's a great point. Yes, the curvature of each of these surfaces is assumed equal, right? In other words, the vibronic frequency here is equal to the spacing of vibronic frequency here.
So in sorry.
No, I'm just saying it's often observed, in organic materials that you do see that close association between those. So no surface is completely harmonic. I mean, it's always an approximation. And if you go high enough in energy, these things will become like Morse potentials, right? And so there'll be a change in the frequencies.
Yes. So in that case, in case you are forced to adopt two sets of frequencies for the two surfaces, so in that case, in your work, have you had to use some other sort of parameters to characterize the displacement?
So, excellent question. First of all, yes. As you'll see in the model that we're gonna show you, it doesn't really matter that the frequencies are the same. Again, it's just in this case, it's as I said, it agrees often with experiment, but of course, if you look hard enough, they won't agree perfectly. Usually within a couple 5% or so. But if you want, but I'm sure there must be examples where they disagree more than that. And if you want to, so the model that I'm going to show you is flexible enough to include that. Yes.
I see. And just a second question. Second question is, if you actually looked at some of the systems, this is coming from a recent experience. Some of the low frequency modes seem to have pretty high Hwang risk factors compared to the, the CC stretch that is so prominently appearing in some of the spectra. So how do you correlate the sort of trends with what appears as 1400 and 1200 vibronic progression versus, through calculations which show you that some of the really low frequency modes have a higher Hwang risk factors than the ones
at 100. Another great question. We have considered those as well. The basic idea with this, and actually you can show it almost quantitatively, is that if you have a very low energy mode, so these are 1400. So suppose you had a 100, wave number mode. So these are typical intermolecular vibrations and vibrations and things like that. Acoustic type phonons. And if you have these low frequency modes, then they can often be, or they can be treated kind of like in a static way. You can imagine that this motion is so slow that if you took a snapshot, you have all these different conformations. And then if you just consider those to be inhomogeneous broadening, you can actually get a very accurate, incorporation of that mode. And so if you have a low frequency, high HR mode, that'll increase the width of these various peaks, right? Because the width of the mode, the slow mode, is tiny compared to the vibronic spacing here.
I see.
And so, yes, you can consider it like inhomogeneous disorder. And that's almost, and actually in some of the older works, if you go back to Schreiber and Toyozawa, there's like a series of papers, and they treat it like Gaussian inhomogeneous broadening that depends on temperature. So as you increase temperature, increase the phonon occupation, you get a bigger, wider Gaussian.
Okay. That's very helpful. Thank you.
All right. So we go back to the bowling ball, right? So the bowling ball on a hardwood alley is like a weakly coupled. There's very little exchange of energy between electronics and the vibrations. This would be Kasha theory, right? You can neglect the vibrations. Just forget about them, and everything, all the energy goes into the ball. Well, that's not so simple in soft organic materials where there's a significant exchange of energy, because you can consider it to be like a bowling ball on a mattress. Now, we all know that a bowling ball on a mattress rolls a lot slower, right? I mean, everybody knows that, right? And that's because the energy that you impart to the bowling ball is now shared between the potential energy of a compressed spring and the kinetic energy of a rolling bowling ball. So the actual velocity is much slower than it was on a hardwood alley floor. And so these springs are very much, they're like the nuclear vibrations in molecules. And so if you look at this profile of you can kind of map it. This is like an electronic excitation. This is like the vibrational situation on the electronically excited molecule, and this is like the vibrational condition or situation on neighboring molecules. This is just a metaphor. And so you'd think that if you really want to describe this problem with in molecules, you need a vibronic excitation and you need pure vibrational excitations that surround it, so-called phonon cloud. And so you can define a nuclear distortion field, and I make a joke, and everyone's supposed to laugh, although I can't hear you, that this is called a bowleron instead of a polaron. Okay, so a polaron is a technical type term when you have a composite particle of an electronic and vibration, but because it's a bowling ball, we call it a bowleron. Okay, anyway. So how do we now incorporate this kind of insight that we got from the bowling ball into a Hamiltonian? Well, Holstein did that already. He took the Frankel Hamiltonian and he added terms to reflect vibrational coupling. So this is just pure vibrational energy. Here's that coupling term. You see, when NN, that means you're excited at the end site. And this linear term here represents the shift of that excited potential that I showed you earlier. You also have the electronic coupling. Here's an extension for those of you who don't like nearest neighbor, MN. Could be anything, right? And here's some disorder. We just talked about disorder in that last question. Which is site dependent. And so you can do all this. And the nice thing about the Holstein-Frankel model, or Frankel-Holstein model, is that many of these parameters can be deduced from a molecule in solution, like the vibrational energy. We just look at the vibronic regression, take the nearest neighbor distance or separation in energy. Voila, we get omega vibe. By looking at the relative intensities, we get the Hwang-Riesz factor. Now, the site energies and the couplings are something that we would have to calculate, JMN. You can use any number of quantum mechanical or quantum chemical techniques to calculate the couplings based on transition charges. But in the end, you can parameterize this Hamiltonian very well. But there's still a challenge of basis set. What is the basis set? Now, this is inspired by a paper by Michael Philpott from long ago in 1971. He suggested a basis set, which I call the multi-particle basis set. So I've kind of extended his work in the direction I'm going to show you. So you have so-called one particle and two particle. Instead of going into the nitty-gritty of this, I'll show you a cartoon. And here's a one particle state. They're very easy to appreciate, right? So you have the nth state excited, but since we're including vibrations, you can't just say, oh, it's electronically excited. You also got to tell me how many quanta of vibrations you have in this excited state well. So I need to say which molecule is excited, how many vibrational quanta do you have in the excited well. Wham, that is a complete description. All the other molecules, by the way, are unexcited both electronically and vibrationally, and that's implicit in this notation. So you don't list them. All right, well, you might say that's enough. But if you think a little bit harder, it's not enough, because there are states where in addition to a vibronic excitation, like we had earlier, you can also have a molecule down the road, in here, the N+2 molecule, which is not electronically excited. So we still have a single electronic excitation, but it has vibrational excitations. And this constitutes that phonon cloud that I was just telling you about. So we need to, and more sophisticated notation. The first tells us where the vibronic excitation is and how many vibronic quanta it has, 2 in this case. And the second set of indices tell us, okay, where is the vibrational, not vibronic, vibrational excitation, and how many quanta do we have there? And you notice I don't have a bar on this V. Whenever I put a bar on V, that means it pertains to the excited state well. So in this notation, without the bar, it's in the ground state well. So this is a vibronic vibrational pair state. It's also called a two-particle state, one particle, two particle. Okay, and so these are the states that we include in our calculation. So we build up a basis set for that Hamiltonian. And if you're interested in the coupling between these states, which of course extremely important, you will fast realize that you can have coupling between one particle states, and that coupling results in a movement of electronic energy down this row, down the line, right? With couplings now that are modulated. You see, that's not the pure JC we saw before, but now it's modulated by a Frank-Condon factor. So it's different, but it's not all, that's not the complete story, because you can jump from a one particle to a two particle state with another different modulation. But the cool thing is that if you have this vibronic state, excited state, when it jumps to a neighbor, n to n+1, you see that it leaves behind in its wake a vibration. So in other words, you go from a single particle state to a two particle state, vibration, vibronic. And that's what the electronic coupling will couple 1 to 2. It's a nearest neighbor coupling, 2 to 3, 3 to 4, and so on. Of course, you could also couple 1 to 1, as you see in the top row, or 2 to 2. It's really a quite elaborate mechanism, but fortunately for organic materials, we can stop at the two particle level in what we call the two particle approximation. And it turns out that the parameters that define electronic coupling and vibronic coupling in organics are conducive to a truncation to the two particle level. So if you calculate an absorption spectrum with just two particle states and one particle states, and then compare it to a spectrum where you include also three particle states, you'll see very little difference. So two particle approximation works very well. And now we're at the point where we can finally understand.
Professor Spano, I had a quick question about the previous slide, if you don't mind.
Yep.
So my question is coming, so this is Vivek Tiwari from ISC, and my question is coming from our sort of previous experience on, once you have much smaller aggregates, but if you have energetic disorder, there could be certain kinds of vibrational electronic coupling in such cases where what's happening is, if you think about truncating the basis sets up to a two particle basis set, But let's say I'm thinking about a trimeric aggregate. Then, what's happening is, let's say between the first and the third site, the vibration is leaving a wake on the third site while the electronic excitation is on the first site. So in such cases, would you, since I need to truncate my basis set, would you consider this also a 2-particle basis set, or is that, is the nearest neighbor coupling restricted to remove this as a 2-particle basis set?
No, if you had a trimer, then you could have, the maximum is 3-particle states, as you said.
Yeah.
So the basis set is not that big for a trimer. So I would include the entire basis set, to be honest, and see what the difference is. But I think, which we did in one of our papers, we went up to we had a tetramer, and we went 1, 2, 3, and 4. And again, with the parameters that define organics, okay, where you have a coupling on the order of 0.1 or 0.2 eV electronic, and the vibronic coupling or vibration is around 0.2 eV, that's the 1400, and the relaxation energy as dictated by lambda squared equal 1, they're all comparable to each other. And in that little region of phase space, it turns out that the 2-particle will do very, very well. Now, if you increase the coupling a lot, then eventually 2 particles break down and you're going to need your 3rd particle.
Sure.
So I'm not saying, yeah.
Sorry. So it's a combination of 2-particle plus, it has to be nearest neighbor. So, the wake cannot be left on the third site. Because, I mean, that would also
be... yeah. Again, I'm just making it simple here with nearest neighbor, but you can jump. This picture just has nearest neighbor. You can jump from 1 to 3 with a J and then leave a wake on that. That's certainly allowed. Again, I'm just trying to simplify it, but you're right. If you do extended near electronic coupling, you'll have much more elaborate type of transfer, and right. But anyway, so let's continue then. And now this is the most important part, really, the vibronic signatures for H aggregates versus J aggregates. So if we now incorporate the vibronic coupling, you remember before we showed those particle in a box like energy dispersion diagrams. Now we have a dispersion or an exciton band for each number of quanta. For each of these we call these vibronic bands. So all these states here have in common a single or actually no vibronic quanta in the excited state. And we can still form these exciton states, these K states, and make a band. In these sets of states have in common a single vibronic excitation in the excited well. And we can still make an exciton band. And these states have 2 quanta in the excited. These are just single particle states that are delocalized. That's why I have the 0th order. Of course, we have to mix with these 2-particle and even 3-particle if we had to. But the basic idea is already present at the single particle level. And because the coupling is positive, each one of these bands has the oscillator strength, just like in the dimer we showed earlier, on the top of the band, right? And so this is the state that absorbs, this is the state that absorbs, this is the state. So there's still a blue shift of each vibronic peak, as consistent with Kasha. But the emission, which I didn't really talk too much about before, is really profoundly affected. And this is the most interesting thing to me. Okay, if you look at an H aggregate, right, the bottom state, remember, that has all those nodes in it, right? So it's K equal pi. Now, we said earlier that it can't, Kasha said that it doesn't emit at all, right? But if you put vibronic coupling in, that only pertains to the 0,0 emission. And it's easy to see that because if you see this is K equal pi, and the ground state, which is the electronic ground state with no vibrations, that also has no momentum. You can't go from K equal pi to K equals 0. This just violates conservation of momentum. And so that's one way of saying you can't get a 0,0. But you can, I call it wiggling out a photon. You can get a photon where it terminates on the ground state, electronic ground state with 1 vibration. These are like phonon states because the K equal pi state can terminate on a Q, where Q is a wave vector of a phonon, Q equal pi. And so you still get the satellite, the sideband, 0, 1, 0, 2. So whereas Kasha said you get no emission at all, when you incorporate vibronic coupling, the new way of seeing this is that you get no 0,0 emission, but you still get sideband emission. So a hallmark characteristic of an H aggregate is if it's an ideal H aggregate, 1 molecule per unit cell and so on, it will ideally have no 0-0 emission. It
Quick question. Frank. This is also kind of interesting because there are lots of molecules where people try to design large Stokes shifts, right? And is it also confusing from that part that you might be looking at an aggregated molecule when you're looking at the emission coming out that appears to be largely Stokes shifted and appears to have the vibronic as well, but it's not from the monomer. So there are molecules where people are designing large Stokes shifted monomers, right? Monomer molecules, and the confusing part is that sometimes your aggregate could be emissive and hence lead to a larger Stokes shift. So
yeah, I mean, you can have, so how do you distinguish between the two? Right. In the molecule, in the current situation here, where you have an H aggregate, you normally will not see a zeros. The complete absence of 0-0 is an ideal situation. Right. You have a little bit of disorder, torsional strength, deviations, whatever. You'll start to, and I'll show examples. You'll grow in some 0-0, but you will get a Stokes shift basically due to the fact that the emitting state is here and the absorbing state is here. So all that energy difference would be interpreted as a Stokes shift. If you have a single molecule, you would be erroneously saying, oh, we have a giant Stokes shift in this molecule, but really it's coming from the aggregate. So it would have to, you require a lot more experiments to really parse out whether you have a molecule or an aggregate. Okay, so we got these features for an H. Let's go to J. J, everything flips over. Now the optical intensity is on the bottom of each of these vibronic bands. You still have these vibronic excitons, right, where delocalized excited states, which include various number of vibronic excitations in the excited state well. And now when you look at emission, instead of nothing, you have a lot, right? This is analogous to the superradiance of in the Kasha model. You have a enhanced 0-0 emission, but you still have sidebands that are not enhanced. And in fact, what I'll show you in the next couple of slides is that if this peak is enhanced, which it is, as I showed you before, it goes by N, and this peak is not enhanced, then you can take the ratio and pull out what we call the excitonic coherence number, which is related to the coherence length. And this is a concept which I have not discussed yet, but coherence is a huge topic now. It was huge in what was called quantum biology and other things. How wave-like is the excitation, and can we exploit that wave-like nature to enhance transport and other things? So this is a direct measure of the coherence length for a J aggregate. I'm going to say a lot more about that soon. All right, so vibronic signatures, we're going to begin with a single molecule which has a unitary Huang-Reis factor. Again, I showed you that's important because now the first two vibronic peaks are equal to each other. So now what happens when we increase in an H aggregate, right, H, when we increase the bandwidth, like that other figure we showed, when we just had H and J without vibronic coupling, now we have it with. And there are some really important features that you observe as you increase the coupling between molecules. This has 20, I think this was an aggregate of 20 molecules here. And so what you see here is, despite the fact that the ratio between the first two vibronic peaks in absorption is equal to exactly 1 when you have no coupling, when you have a single molecule. As you increase the coupling, you see that the ratio drops significantly below 1. So that ratio is telling us something about the strength of the coupling. You also notice that the emission is completely devoid of the 0-0. And here's this Stokes shift that we were just talking about, right? All you see is 0-1. And you also see that the emission starts to go away as you increase the coupling until you get to the point where there's virtually no emission left. And this is exactly consistent with Kasha's model. So you might say, well, how do you get Kasha when you have vibrations? Well, the vibronic coupling, or the electronic coupling, right, is so strong here that when you excite a molecule, it doesn't have time to relax in the excited state well, it jumps to a neighbor electronically. And so you can neglect vibronic coupling in an approximation. And this is kind of like what happened. This is a single blue shifted peak, right? Now let's see what happens in a J aggregate, right? Everything's always opposite. So if you're ever trying to you ever get confused at H and J, if you know H, you know J, you just take the opposite. So this ratio now, instead of decreasing with increasing W, or bandwidth, now it increases. You see, it's going up and up. The blue spectrum is absorption. You see it starts out at 1, then as we increase the negative coupling, right? It's a negative coupling now, but we increase its magnitude, and you can see that now we are having an absorption, which with a ratio which is now increasing with coupling. And if you look at the emission, the red, right? Instead of disappearing, it just gets it remains prominent. The 0, 0 is prominent, and also the 0, 1 is prominent. Again, it's this ratio that we're going to make a big deal about in the next couple of slides. So now I'm going to just take a little breather and show you how an experimentalist can use this information. So let's see, we have 20 chromophores. Again, we have we have our ubiquitous vibration. We have lambda squared equal 1. We're going to consider a H aggregate and a J aggregate. We're going to have positive and a negative coupling. So here's similar to what I just showed you. Here's taking the coupling 175, 350. We see the vibronic the peak starts to diminish such that the ratio decreases. This is an H aggregate. But it turns out that exactly the opposite in J aggregate. So if you use perturbation theory, you can derive a very simple expression for that ratio. Okay, so I'm just using perturbation theory, and you can see from the structure of this ratio, this fraction, that if JC is positive, the numerator will decrease as JC gets larger and larger, and the denominator will increase, so that this ratio overall will decrease. And that's exactly what happens in an H aggregate. If you change the sign of JC in this expression, now you have a minus and make it negative, you have a minus minus. Now the numerator increases as the magnitude of JC increases, and the denominator decreases, so that the overall ratio increases exactly as you see here in the J aggregate. So from this ratio you can measure in the laboratory, you can use this expression to pull out the sign and the strength of the coupling. And that's very useful, right? So it's a way of looking at a spectral signature and deducing the strength of the electronic coupling. So now I will caution you that this simple formula is specific to lambda squared equal 1. If you look at my recent Chem Review paper, or even earlier papers, but it's easier to see there, we generalize this for other Huang research. It's a more general formula. I'm just not going to show you all the details. I just give you lambda squared equal 1, but it will, these coefficients will change when you deviate from 1. So let's show in practice how this works. So here's a beautiful, what I would say is a J aggregate formed by these linked parylene units, right? So you start with a monomer, then you have a dimer, and then you have a trimer. If you look at this, if you look at the transition dipole of each unit, it's along the long axis. So as you build up these linear aggregates, you have a head to tail arrangement of dipoles. So this should look like a J aggregate, right? You also notice there's a twist here, so you don't have to worry about extended conjugation. You can treat these almost as independent absorbers, okay? And if you look at the experiment, that's in these dots here. This is from Langhals. It's also shown later by Wasilewski's group. But you see when monomers in black, dimers in blue, trimers in red. You see how that ratio dramatically increases. So just like a J aggregate, also redshifts. So the vibronic theory is saying that this is clearly a J aggregate, which you can have readily have deduced based on the structure. But even more, if you look at the monomer spectrum, again, you don't get lambda squared equal 1 because these two peaks are not equal, but it would be something like 0.65. And if you adjust that perturbation formula for this lambda squared, you get a formula like this. And so now using this formula, I can pick out what the coupling between nearest neighbors is, right? And if I do that, I get from analysis of this spectrum about negative, because it's a J aggregate, 0.045 EV. But then I can go ahead and calculate this coupling with quantum chemical, TDD-FT methods, using the atomic transition charges. So it's a pretty sophisticated way of doing it. And I get a value which is close, right? And so the deviation is probably because this is a perturbation expression. And even in these spectra, if we wanted a better ratio, we have to do it beyond the first order. But we get pretty good agreement, right? And so from that one spectrum, we can pull out things that we know it's a negatively coupled J-type aggregate with a coupling of order of 0.05 EVs. So that's kind of nice. And if you take the same chromophore, but you arrange it because it's covalently bound to this linker group to side by side, you get H-like aggregates, right? And this is Wasilewski. And you can also measure the dimer would be 0.62, and then the trimer is 0.53. So you see how the ratio is going down as you now increase dimer to trimer, whereas before it was going up, now it's going down. J goes up, H goes down. And if you use the appropriate perturbation expression, you get around 1/10 of an EV, very close to what you get computationally. So it's useful. This is a very useful technique. We applied it a lot to these P3HTs because of their importance in OPV cells. Here's two different spectra spin cast from different solvents. So you get different ratios here. And those different ratios reflect different couplings because you have different morphologies. And so using our ratio formula and setting the ratio to these two different values from these two different solvents, we can pick out two different excitonic couplings. First of all, they're H aggregates, right? The coupling is 120 MeVs in the chloroform and only 20 MeVs in the isodurine. That's because they're different morphology. I can go into that in great detail, but I just want to show you now that we can use this absorption formula to get important information. And go back to our carotenoids. We said before that this was looking like an H aggregate. And if you do a calculation with a morphology that is a twisted or a chiral linear aggregate with these parameters, you beautifully can regain this. Now, notice you can't use the perturbation formula because it's a very strongly coupled H aggregate. There are only 3.5 angstroms between nearest neighbors. The coupling is about an EV, it's huge, and that's responsible for this huge blue shift. So you can get away with the interpretation of the spectrum based on Kasha theory. However, this red spectrum that I showed you earlier for lutein diacetate, not so simple, all right? So, but the theory beautifully agrees with it, but what kind of structure did we have to envision? Now, this is a tightly, the lutein without the diacetate, the strongly coupled H aggregate, it allows for hydrogen bonding because this is an OH group. And so it's tight. But when you have diacetate, you don't have the hydrogen bonding anymore. And so Zilla speculated that you had these liquid crystal type conformations. And so we adapted that in our analysis. And so what we found was that this is in fact, this diminishment of the A0001 peak is a reflection of the coupling between these two layers, where each layer is twisted relative to the layer below it, kind of like in a cholesteric liquid crystal, which is what was proposed by Zilla. But it agrees very nicely with our calculations. And I really can't say much, maybe tomorrow I'll say it, but you might be saying, well, what about the interactions between molecules within a layer? Why do you emphasize just the interlayer? Why not the intralayer? It turns out that we have a very interesting example of a null aggregate for the interactions within a layer. They almost all cancel out. They're side-by-side H's and head-to-tail J's, and they kind of all cancel out. And when the smoke clears, the coupling is still dictated or dominated by interlayer, and that's what you're seeing here. And so the formalism is pretty powerful for interpreting the structures based on the absorption spectrum. I want to now just talk about photoluminescence for the rest of the talk, and then we'll be finished. The opposing nature of J and H also extends to the photoluminescence. We saw earlier that H aggregates had no 00 and J aggregates had major superradiant 00s, right? Now, if you increase disorder, you might ask what happens. In H aggregates, when you increase disorder, you break symmetry and you allow 00 emission. In H aggregates, you add disorder, you decrease the coherence of that very superradiant state, and it goes the other direction. You decrease it. Okay, so opposing behaviors in 0001 increase with disorder in H, decrease with disorder in J. You could also look at what happens when you increase the temperature on an otherwise ordered aggregate. The 00 now can gain intensity in an H aggregate because you can thermally activate that K = 0 state, which is sitting on top of the band, right? But if it's weakly coupled H aggregate, you can reach that band with a KT, which is comparable to the bandwidth. And so you can start to increase the 00. Whereas in J aggregates, once you increase the temperature, you depopulate that strongly emissive K equals 0 state that's sitting nestled on the bottom, and now you decrease. So all different, exactly opposite behaviors. Is this observed in nature, right, in experiments? So back to P3HT, we see the emission spectrum is this beautifully structured PL, right? But if you look at the experiment, the 0001 increases with temperature, very nicely in agreement with what I just showed you. Now, another example of a different example, the contrasting example of J aggregate would be found in tetrazine. These are herringbone-like lattices, and we could give a whole talk on this, but basically they behave like J aggregates. And if you look at the emission as a function of temperature, this very dominant 00 peak, which is characteristic of J aggregates, decreases with temperature. Increase with temperature in H, decrease with temperature in J. Okay, so how do we understand this? And this is probably the most exciting properties of these aggregates when you talk about coherence. And this is how I want to end this discussion on this exciting topic of how do you determine how coherent molecules are in a situation like a condensed phase organic from photoluminescence. And it turns out that whereas absorption reports on the strength of the coupling, I showed you all those examples, photoluminescence reports in some cases, for J aggregate, directly the spatial coherence. So let's try to understand that. So here's a PL spectrum. Here's what it is, right? So you have a J aggregate with a very strongly enhanced or superradiant 00, and an H aggregate ideally giving you no 00, right? But you have these active sidebands. This is a review of what I said earlier. So, and again, what I said earlier is that the 00 emission is coherent. If you calculate this transition dipole, like we did earlier, you'll see that it's a coherent sum over the molecular dipoles. Now I put in Frank-Condon factors and everything else, but it's basically what we said earlier. Remember, somebody asked me about whether this, if they weren't all in the same direction, how do you do it? Here, we generalized it, so they don't have to all be in the same direction, but let's assume they're in the same direction so that mu is, the transition dipoles are just uniquely oriented. This is the square of a sum. So this will be sensitive to coherence. This will scale in the optimal case as the number of molecules in the aggregate. Now for a J aggregate, but for an H aggregate, this state has all these nodes in it, right? The lower state for an H aggregate is K equal pi. So all these coefficients will change sign every molecule, right? And it will cancel and be subradiant. So 00 vanishes. And again, as I just said, in a J aggregate, the opposite happens. It scales and increases with size. So very different, exactly opposite behaviors. If you look at the sideband emission, there's no end scaling or no coherence. And you can see that from the structure of the line strength when you now calculate the transition dipole between the emitting state and the state which has one vibration, right? Somewhere on those molecules, that's a 0, 1, you'll find that it doesn't look like the square of a sum, it looks like the sum of a square. And so that's always incoherent. And so the upshot is the 00 senses coherence, the 0, 1 is completely oblivious to coherence. So the ratio is then a measure of coherence. Again, the numerator senses coherence, the denominators give a crap about coherence, so the ratio should then depend on coherence. And a ratio is something you can easily measure. So let's see how this works a little bit more deeply. A way to describe how wave-like the exciton is through its coherence function. And it's this function here. Others have used it. It's basically telling you this B dagger B is basically a coherence operator, right? Where you're sensing the coherence between molecule N and N plus S. And so the coherence function as a function of the distance or the separation between these two operators, you sum over all N and you get an idea of how wave-like this excitation is. Okay, so the broader this coherence function is, the more coherent it is. All right. Now from the 00 emission, you can show, I'm not deriving it, that it's just the sum of the coherence function over all S values. And the coherence number is the sum over S of the absolute value of this coherence function as a function of S. I'm not deriving these, so don't be upset if you don't see how they arise. Now, in the J aggregate, we said earlier, you have a perfectly coherent J aggregate. The coherence is completely uniform if there's no disorder over the entire aggregate. So this coherence function is completely independent of S, and it extends over the entire aggregate. So if I look at the 0, 0 emission, I just sum up all these numbers and I get my factor of n. You see, if I do a coherence number, the coherence number should be the actual number, and it is. Okay, now in an H aggregate, you also have a lot of coherence if there's no disorder, right? Except the fact that since emission is coming from the lowest state, which has k equal pi nodes, so coherence functions develops an oscillation, just like the k equal pi wave function. It has to. And so if you now calculate the 0, 0 emission, you sum all these coherence values for each S, you get 0. All right, but don't say that, oh, since you don't have any 0, 0 emission, you have no coherence. It's still fully coherent, but with a k equal pi type coherence. And that's reflected in the coherence number, because we're summing the absolute value of C sub S, so that gets rid of the sign. And so this is still coherent over the entire aggregate, except that it's a k equal pi state instead of a k equal 0 state. So it has no 0, 0 emission, yet in an H aggregate, it is fully coherent. It's exactly the opposite of J. Again, in a J aggregate with no disorder, you have full coherence reflected in the fact that the coherence number is n, and that is completely reflected in an enhanced 0, 0 emission, which also scales at n. In an H aggregate, it's still fully coherent when there's no disorder, except the 0, 0 emission is now 0 because of this destructive interference. Still the same coherence number. So how is it reflected in the photoluminescence? Let's now focus on J aggregates, because that gives us the superradiance. If you increase the number, you see the 0, 0 goes up, 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 right? Because it's sensitive to coherence, where the sidebands don't care. There's nothing going on. They don't know whether it's 5 or 10. They're completely oblivious. And so this ratio is telling me the coherence number for a J aggregate. So again, if there's no disorder, it's the 0, 0 scales as n. But the 0, 1 emission, I didn't show you this before. You can show exactly analytically that it scales as the, with this expression here, C of 0, the coherence at 0 times lambda squared. So this is probably the coolest thing. If you take the ratio, this is completely analytical, by the way. The ratio is always n over lambda squared, no matter what the exciton coupling is, no matter what the Klein-Reis factor is, no matter what the vibration is. This is a rigorous result, which I'm very, very excited about, because it tells you that no matter, in a J aggregate, it's restricted to J aggregates. If you take this ratio, which is the simplest calculation, divide that by that, and that is equal to n over lambda squared. So if lambda squared is 1, that ratio exactly gives you the coherent number n. Okay, that's an exact result. And it's also very useful. It could also extend to any situation where you have a symmetry allowed emission from the lowest state, like in these herringbone aggregates. So it's a very useful formula. But you might say, let me anticipate the question. You're going to say, well, come on, Frank, this is a completely ordered aggregate. So that doesn't really exist in nature. What happens when you add disorder? You still have some nice result here. You still have the ability of the PL to report coherence. So I've taken 60 chromophores and I've added site disorder. So I'm fluctuating the site energy like crazy. Look at that. I'm increasing the deviation as I go down. So this is a standard deviation of a Gaussian distribution of site disorder. So this is disordered, this is more disordered, this is even more disordered still. What happens to the coherence function? Before I said the coherence function for an ordered aggregate was flat across for a J aggregate. It was completely consumed all the absorbers, right? It was large. Now I see, as I increase the disorder, you see how it's starting to localize. The coherence function gets narrower and narrower and narrower, and the coherence number is dropping. So the big question is, does the PL ratio reflect the drop in coherence number through this ratio? And in fact, it does. there's a very strong correlation. It's almost exactly equal. If I take this ratio, I will get the coherence number that I would get from an exact calculation. So that ratio formula is quite useful for J aggregates. You might also say, well, what happens if I have a thermal distribution? What if I heat it up? Well, I can now take the coherence function averaged over a Boltzmann distribution of emitters. And again, as I heat it up, the coherence gets narrower and narrower. The coherence number drops 18, 8, 3. And the coherence number can be gotten again by the same formula, but now using a thermally averaged coherence. And does it reflect, is that reflected in the PL? Again, yes, an astounding yes. The ratio gives you the coherence number, which is now determined by thermal distribution of emitters. And so it's very useful. And I'm coming now to some examples, and then we will end. I don't know how much time. I think we went way over 60 minutes, but
we have 5 minutes. Don't worry about it, Frank. Yeah.
Okay. So tetrazine. Now, Chris Bardeen, I worked with him on tetrazine, and you can see here in the experiment, if you look at the emission now, it's very J-like, right? It's got a dominant 0,0, a much less intense 0,1 emission. If I increase the temperature, it drops like a rock. And so our calculations reveal the same exact thing. And if you use this simple ratio formula, right, it's very simple. Just take the ratio. You can say that at 4 Kelvin, we have a coherence number of, 5, 6, maybe 10 different molecules, which is not that large, right? But it's revealed so that PL is reporting a coherence. So that's kind of nice. This is a paper which I discovered a couple of years ago. It's the world record of the coherence number for as related to the PL ratio. So if you look at the PL ratio of, this is a parylene-like molecule called PTCDA, and it's flat deposited face down on potassium chloride in a very, very ordered way. So these authors did all the structural analysis, and they showed that they know the packing pattern, but it's very, very ordered. And then they looked at the photoluminescence at different temperatures, and you can see at 6 Kelvin, 0,0 is huge, and the 0,1 is tiny, right? As you increase the temperature, the relative ratio increases because you see now the 0,1 is larger. And so what they did is they plotted now what they call the enhancement factor, but this is just the ratio. This is the 0,001 PL ratio. You see it drops like a rock with increasing temperature. So very J-like behavior from these which would arise from this head to tail negative interaction that you would have in these nearest neighbors. And so the coherence number here around 10 Kelvin is about 50. So this is the best example. Now I have examples of polymers that can actually do even better than this, but that would be a talk for another day because we're extending our model to include polymers. And so just to round out everything, I don't want to just say everything is J aggregates and we can neglect our poor H aggregates. H aggregates are interesting too, but the behavior is opposite, as I said. If you now look at disorder on the ratio, when it's now here we're increasing the disorder as we go up. So here we have really disorder. You can see it in these deviations, right? This is quite ordered. This is very disordered. But now instead of the 0,0 decreasing with disorder, the 0,0 grows with disorder. Okay, exactly opposite of the J aggregate. So again, even though you don't have a simple formula, that ratio formula where the coherence or the ratio 0,001 was the coherence over lambda squared, that's only for J aggregates. You don't have a nice simple formula for H aggregates. However, you can still do the analysis like we've done for P3HT. And you can see that, as I showed you this before, in the experiment, the ratio increases with temperature. And here on the bottom are some of our calculations, which show that, yes, indeed, these are H aggregates with the 0,001 increasing with temperature. And you can still do an analysis, as I said, of the coherence number. And you get in this stack of chains that you have a excitime, which is only coherent over a couple of chains. So it's quite narrow. So I would say, excitations in the systems that I've showed you are pretty much very narrow. The coherence is confined to just a couple of units. So now I want to summarize. And basically, I showed you vibronic signatures with which to distinguish J from H. In cases where the spectral shift of Kasha can lead to ambiguous assignments, you always have, if you have a prominent vibration, of course you must have that, you have other signatures. And for the absorption, the ratio A1, A2 are the first two vibronic peaks will always reflect the magnitude of the excitonic coupling. In H aggregates, the ratio diminishes as the band goes up, and in J aggregate, does the exact opposite, it increases. So from the ratio, you can pull out the excitonic coupling. The photoluminescence spectrum, on the other hand, that equivalent ratio of the first two peaks is reporting on the coherence length, which is just the number times the nearest neighbor distance, or the coherence number. In J aggregates, the ratio increases with coherence length. We have this very simple formula. We look at the ratio, we set it equal to this, we solve for NCO. And we now know how many, how wave-like the exciton is. In H aggregates, the ratio does exactly the opposite. Then J, it decreases as you increase the coherence length. So there's no simple formula, but we can still analyze it numerically and deduce what the coherence number is. So I just want to leave you with a little enticement for tomorrow's lecture. I mean, we're a little bit tired now, but I have this nice little picture here. And what happens if you have J and H coexisting? And here's a simple example. You have head to tail in this direction so that the J is negative, but in this direction you have side by side, so you have positive. So who wins? And what is the manifestation of that competition between J and H in the spectra? And so I call these Jekyll-Hyde for good reason, right? J and H. And you can see Jekyll, if you know the story, Jekyll was a prominent physician in England, in London, but he loved to dabble with chemistry and behavioral chemicals. And so he develops this potion. This is not Jekyll, this is Jekyll. This is the astounded bystander. With Jekyll himself, when he takes this potion, he becomes evil, becomes this hunched over, what's called Mr. Hyde. And Mr. Hyde goes around and terrorizes London, does terrible things. But it's the coexistence of all of us, of good and evil, of J and H, Jekyll and Hyde, right? I love this analogy because Jekyll is portrayed as, a good person, a philanthropist. He had perfect posture. Whereas once he turned into Mr. Hyde, when he drank his potion, he became hunched over. And it's exactly what you see in the absorption spectrum, right? You see this nice 0,0 peak here, and you see a hunched over, reduced 0,001 emission, which is very similar to what Mr. Hyde looks like when he's hunched over. So it's J and H. And I've done a lot of work in pulling out different examples of J and H. And one example I'll show you tomorrow is related to charge transfer as an additional form of coupling, which interferes with this Coulomb coupling that I talked about today. So there are many manifestations, I guess is what I want to say, of JH or HJ aggregates, Jekyll-Hyde aggregates. And it's really fun to investigate and to look for these behaviors. And also come up with cases which are really cool where they almost completely cancel each other out, right? And in that case, we call it a null aggregate. A null aggregate looks like a monomer in some ways, even though it's well packed, because these interactions are so efficient at canceling. So that's how I want to end it. I want to kind of entice you with the possibilities, right? We're just beginning to explore the impact of morphology on photophysical signals like absorption and emission. And we don't have to go to elaborate means of measuring, 2D spectra or whatever. There's a treasure trove of information already in simple optical probes if you know where to look. Okay, I can't end without thanking people. There's always a lot. I'm just the reporter of the story, but these are the people who did all the work. And most of today's work was older work. And I love this student here was absolutely instrumental in getting everything done. His name is Hajime. His short name was Hodge. And I just thought it was a perfect name for someone to investigate H and J aggregates. So Hodge did a lot of work on that I showed you on the competition with, or the basic H and J in those various systems. Nick Heston was a fabulous student who I'll tell you more about his work tomorrow. And he worked a lot on charge transfer and such, and how that can create H and J aggregates. And I could talk a lot about all these different people. Roel Templer visited me from Groningen, did a lot of work. We got a lot of papers. He is now at Northwestern University, starting his assistant professor career. So anyway, lots of very excellent students and collaborators. What could I say? These are mostly experimental people who are kind enough to give me data before it was published, so we can work on it. Some of these are theoreticians, like, let's see, where's, David Beljohn, you may recognize the name, very, very prominent theoretician in Mons, Peter Bobert from Eindhoven. And so, without these people, nothing happens. Of course, funding is absolutely essential as well. And I've been very, very lucky to get funding from NSF over the years for doing these things. So, and a giant thank you for all of you out there who put up with me for this much longer than 1 hour talk. But I swear that when I practiced it, it was 1 hour. So anyway, thank you very, very much for listening. And thank you again for inviting me.
Thank you. So thank you, Frank. Thank you very much for this very excellent and lucid presentation. I think all of us got immensely benefited with the very basic and fundamental optical properties of this pi-conjugated system. So I think there are many questions have been already asked during your presentation. I'm sure you must be very, very tired now, early morning.
Okay.
So
I don't want to go back and look at the election results. So if you want to ask,
that's fine. So there are few are in chat box. If you are fine with this, otherwise we can continue the discussion tomorrow.
I can take a couple of questions now if you like.
Go ahead. So Devdas Ray, would you like to start? You can ask the questions. I think you are one of the panelists.
Devdas, could you unmute?
Yeah, can you hear me?
Yes.
Yes, I can hear you.
Hi, Professor Frank. This is very beautiful presentation that you have presented today. And I'd like to thank your organizer, Jatishman, and other member. Yeah, so it's really interesting. And I've been working in this kind of field now, particularly the photoluminescence on the aggregates. And also I work on your materials that gives you thermally activated delay fluorescence and phosphorescence, all the kinds of things I'm doing. So my systems are, when I do the experiments, my systems are, as I said, one of the questions previously, the systems basically are two-state nature. So basically systems are having kind of a two part of the organic materials. They are connected by a covalent bond. Their dipole moments are, individually there are some angles. But when I see my absorption spectra and emission spectra, they are broad and they are always in the red side, means in the longer wavelengths after excitations. So it's difficult to understand whether it is a J aggregate. Of course, it is not a J aggregate. But yeah, so if you can explain a little bit about that if I look at your crystal structures, your intermolecular distances and the packing of the molecules, because I cannot find any kind of parallel orientation of your transition dipoles. So they are kind of an angular orientations. So when I look at my experiments, like your absorptions and emission spectra, specifically absorption when I add water, try to form the aggregates. And I look at that, these are the kind of redshifted bands. But since your transition dipoles are not oriented parallelly, they are kind of an angle. Maybe it could be a T aggregate or something, I don't know. So if you can elaborate a little bit on that direction.
So are these, if they're closely packed, is that what
yes.
Yeah, so I think tomorrow's talk might help illuminate some of your question. But yeah, it's actually much more interesting or more complex in a way than what I've showed you already. One of the things about the Kasha theory, in addition to not including vibronic coupling, he also limits or focuses entirely on Coulomb coupling. But as we all know, when you have tightly packed molecules in a crystal, wave function overlap will contribute also to an effective will just lead to interactions between molecules. And in the end, you have to incorporate all sources of coupling, and that could give you a rich kind of array of behaviors, as I alluded to in this last slide with JH aggregates. So you really, and as I'll get into, I'll give you a little teaser for what I'm going to show you tomorrow. If you do include these other interactions, which are basically pi overlap type charge transfer, they are extremely sensitive. I would say hypersensitive to orientation. So whereas Kasia says, okay, you start side by side, you got to move a molecule almost a half a length of the molecular distance in order to go from H to J. It's a significant, displacement from side by side to head to tail. But when you talk about H and J with respect to charge transfer, intermolecular charge transfer, and I'll, if you don't understand that, it'll come obvious tomorrow. I could go sub-angstrom and convert between H and J. So just a tweak can take me from a beautiful H to a beautiful J. And that is, so, in other words, if you know the packing with X-ray, if you know the X-ray structure, and then do your calculations of your wave functions, using TD-DFT or whatever, and then calculate your resonance integrals and things, that's the kind of level of attention you have to give it in order to really understand the photophysics. I mean, it's not enough to just, calculate transition dipoles. It's far more than that. And then, as you said, if you have transition dipoles which are not aligned, that gives yet another possibility of David-Weiss splitting. So, it all comes together, believe me. It's not, it all comes together to give, the association between theory and experiment is still good, but it requires you to dig deeper into the very nature of the electronic interactions. And that, it's too simplified to always go and say, oh, it's just transition dipole. That is oversimplified. It's much richer than that.
Okay, thank you very much. So I think there are a few, there are many already. I will read out for the grad students. One is from Kannad Mujumdar. While analyzing an aggregate absorption, how do you identify whether it has a pure vibronic progression and not one having underlying population inhomogeneity?
How do you know if it's, again, I didn't hear exactly. Can you just repeat that last part?
The last point, and not one having underlying population inhomogeneity.
So you have a vibronic progression and possible, which also inhomogeneous broadening. I don't, you could have both. Is that the question?
Yeah.
So basically, look, and none of this analysis would be possible. So if you have inhomogeneous broadening, it'll increase the width of your vibronic peaks in your absorption, right? If the disorder is large enough to obscure the progression so that you can't reliably, even measure individual peaks or the distance between peaks, which give you the vibrational energy. If you have enough disorder, then it'd be very difficult to use these techniques. Now, I never mentioned this, but now I think this is what you're alluding to as well. You might say, well, you have this ratio, which is basically between the 0, 0 and 0, 1. And you've done it, you've got this nice little perturbation formula, but doesn't it care about whether you have inhomogeneous broadening? And the question is, yes, but the inhomogeneous broadening enters in a higher order. And the way to think about it is you have these vibronic bands, right? And they're well separated. Well, they're separated by a vibrational quantum, but again, perturbation theory requires the electronic coupling to be weak. But if you add inhomogeneous broadening, it mostly will couple states within each band. And it won't transcend interband. So these interband effects, or the ratio and such, are fairly insensitive to the presence of inhomogeneous broadening. And so you can use that ratio formula without worrying about the fact that there's inhomogeneous broadening, which is contributing to the width of those peaks. And to show that, in the Chem Review paper I wrote with Nick Heston, we show, increasing if you increase the disorder, and it remains smaller than a vibrational energy. If it got bigger, then you wouldn't even have a progression. But if you increase it, the ratio hardly changes. Okay, so disorder will mix states within a band, so they'll create band widths, but they will not higher order only to mix states between bands, and so you get away with having not to really worry about it. So it's a fortunate structure, fortunate that you can make these simple or derive these simple formulas without having to worry too much about it. But if you want, you can go to the papers and see.
Thank you. And we will end.
Very good question.
Like last, I think Mahesh, maybe we'll end this today's talk with the last question with Mahesh Hariharan.
Yeah, thank you, Satish. Thanks, Frank, for this very informative and excellent talk. I have a couple of concerns. Is it something that is known in the literature? So one aspect is, let us say, the kind of aggregate that you have shown, which Mike has explored on PDI trimers, both in the J and H format. If you change the solvent, will the solvent influence the signatures of signatures that corresponds to H and J aggregate? So this is one question. And another one is, will pressure influence the coherence that you have discussed towards the end of the lecture? So these are two separate questions.
Yeah, so solvent effects are important, but again, my opinion is that they are, so a solvent will screen differently interactions, right? So you have a polar solvent, more effective screening, and very basic ideas. I would say, of course, you can change the magnitude of a coupling, but to change the sign of a coupling through the polarity of the solvent is something that I would think would be very difficult. I don't know offhand of any literature that would show such an interesting effect. So again, I was kind of cavalierly assigning dipole coupling to that simple formula that point dipole. But in reality, it's a screen coupling, and the screening comes from solvents, and screening will reduce that. And so we'll see tomorrow in a lot of the PDIs to crystal work, you have to screen it because the dielectric constant's on the order of 3, right? 3 or 4. Yep. And so if you don't get the raw electric field or the raw coupling, you've got to screen it. And so yes, changing solvent could change the magnitude of that ratio or the ratio itself, but it wouldn't take it. I don't know. I would estimate 5 or 10% possibly, but it wouldn't change the ratio from being below 1 to bigger than 1. That would be really interesting to go from H to J, or vice versa with solvent change. And I'm not aware of anything like that. And the second question, pressure. Yeah, pressure is something that I think is largely unexplored. There were a few interesting studies. I think Zhenan Bao has done studies of increasing pressure on polyacene crystals and looking at the effects. But pressure can, especially in these hypersensitive interactions that I talked about a couple of minutes ago, that arise from charge transfer. If you can change an H to a J aggregate with the movement of, let's say, 0.8 angstroms, just to pick a number, a sub-angstrom, that might be something that you can detect or enact with pressure changes, right? You put a crystal under gigabar or something huge, hydrostatic, type pressures, or even shearing type pressures, which might even be more interesting, right? So if you can identify a shear direction, say in a pi stack, if you can shear those two molecules against each other and change their longitudinal registry and the overlap of the homos and lumos, yeah, you can see you might be able to induce an H to J aggregate transformation. And that would be really cool. I've not seen that either. So your questions are really good. I mean, they're good points to be looked at, definitely.
Thank you, Frank.
Yeah.
Can I just take one question from YouTube? There are lots of questions and they will be going away. Just one question. I will request Pavitra Nayak, Deepak Dinkar to keep their questions for tomorrow, and we will take it up. But today I will take one question. Aritra Sarkar is asking from YouTube. Hi, sir. Will the coherence length be always higher in J aggregates? Can an aggregate have both H and J coupling? These are the two parts.
Oh, well, the second question, yes, it can have both J and H, and that's something for, I'll elaborate on that tomorrow. But I don't see the first question, which is a J aggregate naturally poised to have greater coherence than an H? I would say that only because in a J aggregate you have the fact that the K equals 0 state sits on the bottom of the band, right? And when you excite a band, energy inevitably flows to the bottom. But if you're at the bottom and you're exciting the bottom, I think you have a chance to observe greater coherence in J aggregates and H aggregates. But as far as an intrinsic reason why you would have one over the other, I don't think there is one. In fact, in H aggregates, if you again regulate the coupling to Coulomb coupling, if you look at the magnitude of the coupling as you do this head to tail shift, the H aggregate, the coupling when side by side is huge compared. You go through 0, and then when you recover the negative J, it never, attains a magnitude as big as H. So from that argument, with a large electronic coupling, that might be able to subdue these forces that would kill your coherence, like disorder and things. You would say H might be better at preserving or at displaying coherence. It's not an easy question, I guess, in the end, which aggregate type would be more conducive to coherence, because there's a lot of things to consider. The world record holder, I haven't mentioned it, and it's a good way to end, is called polydiacetylene. You're going to say, "Ooh, you can't introduce polymer." I'm saying in a single strand of polydiacetylene. Now, I haven't talked about the fact that you can look at a polymer like polydiacetylene as a aggregate of repeat units. Okay, if you allow me that, and if you look at this incredible work of Michel Schott, this is work from 20 years ago, where he takes these diacetylene monomers and he crystallizes them, right? And then he shines UV light and he induces polymerization, but it's because of the steric hindrance, it's such a perfect linear chain that it's practically devoid of any defects, right? And then he looks at the photoluminescence, right? And it's absolutely beautiful. The 0, 0, well, it kills the 0, 1. So it's like a factor of 100, right? That's the world record as far as I go. Now, what does that mean? First of all, it means it's acting like a J aggregate. And so I have this whole other talk, which unfortunately I won't really get into even tomorrow, but you can look at a conjugated polymer as an extended linear J aggregate, right? And so for Schott's almost perfectly linear crystals, right? Or linear polymers, you can really see this J aggregate behavior through the photoluminescence and through this gigantic ratio. And he measures gigantic coherences on the order of a micron, which is insane. Calculations I've done support 1/10 of a micron. So we're still not fully understanding. And the latest kind of contribution to this is perhaps you have something like polaritons, which is a whole other thing. But the fact that you have this polymer exhibiting this gigantic PL ratio shows that there is significant coherence in this J-like construct, right? And then you can really get exciting and have fun with saying, okay, if I have one polymer which is acting like a J aggregate, right? What happens if I make a little railroad, right? 2 running parallel, J and J, and here's now this very strong H that's in a couple of these 2, right? And so now what do you get? Is it an H? Is it a J? Is it an HJ? I've used this really weird, not weird, but really interesting notation because I use HJ, but then I'll use a lowercase to indicate which one is the weaker of the two. So it's a competition, right? And it's hard to say who wins unless you really dig deep. But yeah, so I get excited about this stuff because there's so much potential to really go further and look at some more complex morphologies using the tools that Kasha pioneered, right? And then make, probably predictions about what might be an ideal material for solar cells or for light emitting diodes or something. So we're getting to the point where we can really, really make design, really come up with some design principles. And that's the ultimate for commercial applications. But yeah, it may be a good way to end this talk. So tomorrow, bright and early, I will discuss more about these JH interactions. So if you were intrigued by those, stay tuned, as they say, the same bat time, same bat channel, tomorrow. Okay.
Thank you very much, Frank. Thank you very much. So I will.
Thank you guys again for the invite. Yeah.
Thank you very much, Frank. This was fantastic.
Okay, JD. Thank you guys. Thank you very much, and I'll see you tomorrow.
Yeah. Hope we get Biden, right? By that time.
Biden. Okay, now you know who I'm rooting for. Okay, all right. Okay.